Welcome to The Explainer. Today, we're unpacking the absolutely incredible, highly regulated science behind the single most utilized building material on Earth, concrete. It's literally everywhere, forming the bedrock of our modern world. But hey, it's not just some haphazard mix of dirt and water. We're diving into a fascinating, tightly structured world of chemistry, precision engineering, and rigorous standard procedures outlined in American codes. So how can the exact same ingredients create a structural masterpiece? Or, a crumbling disaster? It's a wild paradox. The basic ingredients, crushed stone, sand, cement, and water, are deceivingly simple. Mixed one way, you get a skyscraper that shrugs off earthquakes. Mixed without care, the whole shebang fails miserably under its own weight. So what's the secret differentiator here? Well, the answer is perfectly captured right here. The difference between good concrete and bad concrete lies in quality control. This is a quote from M. Ramaya, and it hits the nail right on the head. The real magic ingredients aren't the rocks and water at all. They are strict human care, specialized knowledge, and rigorously standardized procedures, like those strict guidelines set by the American Concrete Institute for the entire construction industry. Okay, let's run through our agenda for today. 1. The concrete paradox. 2. Manufacturing Portland cement. 3. The standard mixing procedure. 4. Placing and finishing. And 5. Quality control and codes.
Section 1. Manufacturing Portland cement. The active ingredient.
We start with the modern dry process of cement manufacturing. It kicks off at the mine. Massive limestone boulders are blasted, crushed into tiny fragments, blended with clay or shale, homogenized, and then fed right into a series of preheaters. Finally, it all goes into a massive, tilted cylinder known as the rotary kiln. Now, this isn't just baking, it is a highly controlled pyro-processing system. And inside that kiln, the material is hit with temperatures up to 1,500 degrees Celsius. To put that insane number into perspective, that's the point of incipient fusion, basically the exact stage right before material completely melts into lava. The raw powder actually sinters and partially melts to form a totally new, nodular-shaped substance we call clinker. After it cools down, this clinker is ground into an ultra-fine powder mixed with a tiny bit of gypsum to prevent it from flash setting, and boom, you've got Portland cement, the ultimate binding agent of the modern world. Moving on to Section 2, the standard mixing procedure, following the recipe. So here are the 6 strict stages of the manufacturing process: batching, mixing, transporting, placing, compacting, and curing. According to standard procedures from American codes, if any single one of these steps is compromised, the hardened concrete is going to suffer. The codes literally demand meticulous care at every single checkpoint. Let's zoom in on that very first step, batching. Batching is just how we measure our ingredients. You basically have volume batching versus weight batching. Now, volume batching is super unreliable. Why? Because sand holds moisture, and moist sand actually swells or bulks up. If you just measure by volume, a bucket of wet sand contains way less actual solid sand than a bucket of dry sand. It totally ruins your chemical recipe. That is exactly why structural codes demand weigh batching. It's precise, it's the standard for quality, and modern plants even use electronic sensors to automatically deduct the water weight in the sand from the final calculation. Pretty smart, right? Now think about the water. You don't just dump it in with a garden hose. Specialized measuring cans are a great example of this, reinforcing a critical concept. Water is calculated down to the final drop to hit the perfect water-to-cement ratio. If you add too much water, sure, the mix is easy to pour, but it becomes incredibly weak and porous when it dries. Too little water, you won't even be able to compact it. It's a very delicate balance. Once it's batched, it has to be mixed thoroughly. Sure, small manual mixers are fine for fixing a sidewalk, but modern batching plants use incredibly high-powered equipment. It's all about efficiency and homogeneity. In an advanced pan-type machine mixer, it literally takes about 20 seconds of high-speed rotation to get a perfectly uniform mix, where every single grain of sand and gravel is completely coated in that cement paste.
Which brings us to Section 3, placing and finishing, setting in stone. Okay, so the concrete has left the mixer and entered the real world, and the rules here are strict. American codes dictate that the mixture must remain plastic, meaning workable and moldable, for a minimum of 30 minutes, so workers can actually handle it. But it absolutely must lose its plasticity within 10 hours to become invulnerable to damage from the outside environment. During this tight window, it needs full compaction, usually with vibrators, to force out trapped air pockets, and it desperately needs protection from evaporation, which we call curing.
Now, for massive infrastructure projects, like highways or airfield pavements, the concrete is placed and finished continuously using a really cool technique called slip forming. A specialized machine basically takes the fresh concrete and extrudes it into smooth, perfectly shaped profiles, consolidating and finishing the whole thing in one pass before that setting timer runs out.
And finally, Section 4, Quality Control and Codes, the invisible rules of safety.
Before concrete is even allowed to be poured, it gets tested right on the job site using standard procedures set by American organizations like the ASTM and ACI. Take the famous slump test, for example. You fill a metal cone with fresh concrete, pull it up, and measure how much the wet concrete slumps or sags. This instantly checks the workability and consistency, proving the batch plant sent over the exact right recipe without sneaking in extra water.
But testing the fresh stuff isn't enough. We have to prove its hardened strength. Small sample cubes or cylinders are cast straight out of the delivery truck, cured in perfect lab conditions for up to 28 days, and then they are literally crushed in a massive hydraulic press. It's wild to watch, but it's done to mathematically prove the potential compressive strength of the structural concrete.
Now, because concrete relies on natural mined materials like rock and sand, you're always going to see minor strength variations from batch to batch. You just can't avoid it. So to manage this, structural codes use a normal distribution curve, a statistical bell curve. By calculating the standard deviation of dozens of crushed test samples, engineers can ensure that the safety margins of the building are scientifically met, even with those natural variations. And this all leads to the ultimate hurdle, the acceptance criteria. This is a strict code rule stating that concrete only passes inspection if the mean average strength of 4 consecutive test groups meets the specified limits. If a batch fails this, the work stops immediately. Parts of the building might literally have to be torn down. Quality control, according to these rigorous American and international codes, isn't guesswork. It's an uncompromising mathematical law. Which brings us to the end of our explainer. I want to leave you with this thought. Next time you look up, whether you're in a parking garage, a massive office building, or driving under a bridge, ask yourself, what invisible scientific standards, what precise standard deviations, and what rigorous codes are holding up the ceiling above your head right now? Because as we've learned today, it's not just rocks and water keeping you safe. It's the incredible science of standard procedures. Keep learning, keep asking questions, and I'll catch you next time.